Hey guys, this is Madhav. I've been going through Khan Academy recently, their curriculum on AP Physics PC, and I was a little bit disappointed that they don't have practice questions for the fluid dynamics section. So I decided that I'll just have to create some questions for myself, and these are going to be, well, decidedly much harder than the stuff on Khan Academy. If you're looking for a challenge to see if you really understand buoyancy, then I have the problem for you. So you have this aquarium where there is a sand bed at the bottom and there's a little cube that's lying on the sand bed. It's attached by a rope to a pulley, and then the rope goes on its other end to a buoy, a much larger buoy, a material that is of lower density than the water around it. So there's going to be a buoyant force that tries to pull the buoy up, and if the buoy is, not too dense, then the buoy will be able to rise up even though it is dragging along this cube behind it. So I am giving a bunch of information about the cube, the pulley, the sand bed, and the buoy here, and there's a two-part question. The first part is, what is the maximum density that would still allow just the buoy to barely start rising upwards? If it were any less dense, then it would be able to float away. If it were just a little bit more dense, then no, not enough buoyant force. It's not gonna overcome the resistance of the sand on the cube or the water resistance, and the buoy won't float up. The second part is, if the buoy were made of this particular material, a very light kind of wood, then what would the acceleration of the cube be at the very moment that the buoy is let go and allowed to float up? So if you're looking for a challenge, you can pause the video right here. All of the information is here, the two questions are here, and I am now going to answer probably just this question. It's going to take a little bit of time, so we'll do a two-part tutorial on how to answer the second one. But first, to get started with just this question, what is the maximum density, that density where the system is just about to move but not quite? Well, I'm going to start as ever with free body diagrams, and here the three relevant objects that I want to focus on are the buoy, of course, the cube, of course, and also the pulley. The key thing to recognize here is that, as I said, we're talking about just that boundary condition. Things are about to move, but they're not quite yet moving. So really what we're going to have is the buoyant force of the buoy that is, pushing it up. It is going to be just about the same as the resistance from the water and the friction from the sand acting on the cube. So in this particular question, in this condition, nothing is actually moving yet. This is just saying, like, it's okay, it's maximum density, it could be, let's say, 700 kilograms per cubic meter, and what that means is, if it were just a smidgen underneath that, like 699.99 kilograms per cubic meter, then the system would move. But for analysis, for making these free body diagrams, we're in luck. We can just assume all the forces are balanced. So let me zoom in and try and explain this one thing at a time. Oh, we don't get any more zoomed in. Okay, so I'll just explain it as a whole. Let's focus on this red diagram first. This is for the buoy. So on the buoy, you can see that there's no horizontal motion, so we don't need to consider an x-axis. We're just considering a y-axis. And for the y-axis, there's a force pushing upwards, which is the buoyant force, and that buoyant force is going to be equal to the mass of the water that is displaced by the buoy times the gravitational constant, i.e. the weight of the water being displaced by the buoy. In terms of what is pulling the buoy downwards, first you have the weight of the buoy itself, and then you also have this rope. The tension in that is pulling downwards. Next we move on to this object. This is the pulley in white. You can see that it has a torque, tau buoy, that is pulling upwards. It also has a torque generated by the cube, tau c, that is pulling it right. I defined clockwise rotation to be a positive axis here, and well, as I said, right now nothing is moving. So even though we have this positive direction, the pulley is not rotating. This is just that boundary condition before the rotation happens. So we're not really going to focus too much about the pulley throughout the rest of the question. Finally, this mess over here, let's start with the x-axis and then we'll move on to the y-axis. So this blue dot, it represents the cube, and when we look at the forces in the x direction, well, we have the tension on the rope that is pulling leftwards, and then we have the forces of friction from the sand and resistance from the water that are slowing down that leftward force, that are cancelling out the leftward force in this case. So that's in the x-axis. And in the y-axis, we have to be careful here. So we don't just have the mass of the cube times the gravitational constant, i.e. we don't just have the weight of the cube to worry about in terms of what is pressing down. We also have to think about the weight of all the water on top of the cube, i.e. what is the mass of the water column on top of the cube. If this wording sounds odd to you, let me draw a quick diagram. So let's say we have, the water level up here, and then we have a cube. I'll try to be somewhat 3D, though not too much. So we have this cube here. What I say when I'm talking about the weight of the water above the cube, or the water column above the cube, I quite literally mean directly above the cube. So if I extend some lines upwards for the water column here, okay, this one looks a little bit rougher, but whatever. So if you can imagine this area there you go. If you can imagine that area, all of this stuff in the shaded region, all of the water directly above the cube is pressing down on the cube with its weight. So that's what I'm referring to with the mass of the water column. The mass of the water column being the mass of the water directly above the cube that is pressing it downwards. Next we have, finally, we have the normal force from the sand bed pushing the cube upwards. So we're assuming that it's not floating away, it's not sinking, so the normal force is perfectly offsetting this weight of the cube itself and all the water above it. Now, one quick thing to note, you might have noticed that I put the same tension on both this side of the rope over here and this side of the rope over here. I can only do this in this particular case, not the second question. The reason I can't do it in the second question is, in the second question we are assuming that motion is happening, and if motion is happening, quite clearly the pulley must be rotating, and if the pulley is rotating, quite clearly we can't have the same forces on the left side and the right side. That's only happening in this case while we're talking about this boundary condition when no motion is actually occurring yet. Otherwise, we'd have to have a tension 1 over here and a tension 2 over here, and they would be different. So that is basically the physics of the problem out of the way. all we have to do is brainstorm a bunch of equations that summarize the information in this diagram. I always like making a table because otherwise it becomes a mess and I can't keep track of things. So I'm just going to go through each of these diagrams one at a time, one axis at a time even, and just brainstorm some equations. Not worry about what the solution is yet, we're going to worry about that later. So I'm going to start off with the pulley because it's the simplest. As I said, no motion occurring, both these torques are the same on the both sides. So I'm just going to put in equation 1. Let's not cross out what I'm writing. So how do we do that? Alt Shift 5, there we are. Equation 1 for the pulley. Quite simply, we have the torque from the buoy is the same as the torque from the cube. And we are done. That wasn't too bad. I'm now going to move on to this buoy here because it only has one axis, so I like that. I don't want to deal with this mess yet. So number 2 for the buoy. As I noted here, the positive y-axis is the upward direction is the positive y-axis. So I'm going to put the force, the buoyant force as positive. So that's going to be the mass of the water displaced times the gravitational constants. As I noted, nothing is moving right now, so we could directly assume that this upward force cancels out the two downward forces here. So I'm going to write that as the upward force, it's equal to the sum of these two downward forces, the weight of the buoy and the tension. Now we have some complications here. Do we know what the weight of the buoy is? Well, if I look at the original question, it tells us the volume of the buoy, but we don't yet know what the density is, so we can't combine those two yet to figure out the weight of the buoy. I should say the mass of the buoy instead, but also the weight of the buoy. So I'm going to write down another equation, making that relationship more explicit. So the mass of the buoy is going to be the density of the buoy, this is what we're looking for, times the volume of the buoy that we are given. I should say mass of the buoy here. For the mass of the water displaced by the buoy, that's going to be different. For the mass of the water displaced by the buoy, that's going to be equal to the density of the water times, again, the volume of the water displaced. Now the volume of the water displaced is the same thing as the volume of the buoy, because all of the water that would have been inside this volume here is now no longer inside that volume because the buoy is pushing it away. So we just write the volume of the buoy again here. We don't know what tension is, but I don't see yet an easy way of creating a formula for it, so I'm going to instead move on to the cube instead. Again, one axis at a time when we have these multiple axes. So the first thing that I'll do is I'll again start with the y-axis. So for the y-axis, assuming up is positive and all the forces are balanced, that's what we're doing right now, then the equation is quite simple. For the cube, we just have the normal force in the upwards direction, it's equal to the two downwards forces, which is the mass of the cube times gravity, the gravitational constants. Also we have this mass of the water column. Now how do we calculate that? Well, I'll work through this visually so that it's easier to understand. So we want to find the mass of all of the water in this volume. You can see this volume is a rectangular prism. Alright, that's interesting to note. So what if Well, we know that the mass of anything is going to be equal to the density of the thing, whatever the thing is, so some subscripts will go in there. It's going to be equal to the density, rho, times the volume of the thing. Alright, what is the subscripts that we want to fill in? Well, I defined it earlier as WC for water column, so that's going to be the mass of the water column. What is the density of the material in this volume? Well, it's just water in that volume, so the density is the same as the density of water. What is the volume, finally, in this water column? As I said, it's the same as the volume of a rectangular prism. So I'm going to put in RP. And from basic geometry, a volume of a rectangular prism, it's going to be equal to the base times the width times the height. Alright? So the base here, we were told that the cube is 1 centimeter by 1 centimeter. So that tells us both the base and the width. It is 1 cm times 1 cm. And then the height, we were told the cube is 30 centimeters underneath the surface of the water. So that is 30 cm for the height. Now, I think that we can just leave this for now. I think that we might need to convert the units a little bit later, but for now we can see that the volume is 30 square centimeters. So I'm just gonna leave that calculation over there, 30 square centimeters, and I'll just write down the formula down here. So the mass of the water column that we're gonna be using, it's gonna be the density of water times VRP, rectangular prism, that we just left over here. Alright, we should probably finish out our formula, so let me also add the normal force. It's equal to these two downward forces here, so the mass of the cube plus the mass of the water column times the gravitational constant. Alright, last equation for the cube, we have in the x-axis here, we have that the tension on the left hand side, again, all forces equal right now, nothing's moving, it's gonna perfectly balance with these forces on the right hand side. So I'm gonna write that. So the tension is equal to the friction from the water, aka the water resistance, plus the friction from the sand. And what is the friction from the sand? Well, we have, in this case, static friction. Nothing is moving yet. So we're gonna use the formula for static friction right before an object is about to move, which is the normal force times the coefficient of static friction, mu s. How about the water resistance here? You might have noted in the initial problem we have a very large assumption. We're assuming constant water resistance of 5 newtons per every square meter of cube. Now this isn't too far off when the cube is only moving slowly, like 5 centimeters per second. But as the speed of the cube accelerates, well, as the speed of the cube rises, then the resistance is going to increase quite sharply. So this is a big assumption, but for simplifying purposes, we'll do it for now. So if we did have that assumption, what would the force, the water resistance be? Well, it would be the area of the cube and I showed how to compute that right here. It's just 1 centimeter times 1 centimeter, base times width right here. It's going to be that area times area of the cube times 5 newtons per square meter. Alright, now you might already see a few problems here, which is the biggest one being that some of these are in standard units like kilograms and cubic meters, whereas others are in centimeters or grams, and I really dislike that. Personally, I find it really easy to make mistakes when that happens, so I'm going to convert all of these constants to the units I want first. So converted constants, let me just make a list of those before I do anything else. So what's the volume of the cube gonna be? Well, do we need the volume of the cube? I don't think so, but we do need the volume of the rectangular prison above the cube, so what's that gonna be? We said earlier that it was 30, cubic centimeters, not square centimeters. Let's fix that. So it's gonna be 30 cubic centimeters, but we want it in cubic meters. So what I'm gonna do is I'm just gonna write it out here even. Every time that I would have had a centimeter, I'm gonna write it in terms of meters, and that will help me get an answer in cubic meters. So this is equal to, instead of 1 centimeter, it's 0.01 meters times 0.01 meters times 0.3 meters. What's that equal to? Well, let me write these as fractions so it's a little bit more clear. So 100th of a meter times 100th of a meter times 3/10 of a meter. That's equal to 3 over 100, add a 0, add 2 more zeros. So 300 thousandths of, these are meters times meters times meters, so cubic meters. So I'll just note that down. So this is going to be equal to 300 thousandths of a cubic meter. Alright, what else do I need to convert? A mass of the cube. So 1 gram is a thousandth of a kilogram, so I'll note that. So the mass of the cube is 0.0, or let me use fractions, 1,000th of a kilogram. Anything else that needs conversion? Mass of the water displaced. We dealt with that. The mass of the buoy, is that given in, we don't know that yet, we'll figure it out. We do have to convert the volume of the buoy to figure it out though. So the volume of the buoy is given again in cubic centimeters, so we'll use a similar process to converting into cubic meters. For example, it says it's 1,000 centimeters, 1,000 cubic centimeters. You can imagine this is like 10 times 10 times 10, so 10 centimeters. Let me write that nicely. 10 centimeters times 10 centimeters times 10 centimeters. Alright, same switcheroo as above, write that as a meter. So 10 centimeters is 1/10 of a meter. Again and again. So we get 1/10 times 1/10 times 1/10, 8,000th of a cubic meter. So let me just write that. we have the volume of a cube that is 8,000 of a cubic meter. Sorry, volume of the buoy. Volume of the buoy is 8,000 of a cubic meter. Now we are done. Okay, everything is in standard units. We are ready to solve. But as you can see, there are a bunch of equations to work through, so this is going to be tedious, but it's not going to be hard, right? Because we've done all the physicsing. All the physics that needed to happen in this question has been done. Now we're just doing math, plugging one equation into another. So let me do one chunk at a time. First off, I already said we're going to ignore the pulley. It's not moving, nothing's happening, force is equal, so just never mind this. I will cross it out. Next, let's focus on these chunk of equations for the buoy. So I will highlight these for now to indicate that we're focusing on them. So for these equations about the buoys, you'll note that the main equation, it has these constants, the mass of the water being displaced and the mass of the buoy, that are being defined in these equations down here. So why don't I just take 3 and 4 and substitute them into the second equation. So that's what I'm going to do. I'm going to copy this over. 3 and 4 into 2. That's what we're substituting right now. Copy it over. Please copy it over. And then instead of where I see the mass of the water being displaced, I'm going to plug in this formula. Like so. Where I see the mass of the buoy, I'm going to plug in this formula. Like so. Alright, not too difficult. Now let's focus on the next few equations. Where to get started here? Well, if you may recall, these two equations were about the y-axis only of the cube. So I'm going to highlight these to show that we're going to now focus on them alone. So what to do? Here we see that we have one unknown, which is the mass of the water column. So I'm just going to take this equation and then substitute in this value right here into that equation. So that's equation 6 being substituted into 5. So we take equation 6, copy over this bit into equation 5 right here. Finally, we have this last chunk of equations, so I'm going to highlight these. They're related because they're all about the x-axis. So we're going to look at the x-axis of the cube's motion. The substitutions seem pretty simple here. Just take, except I need to get my subscripts right. So just take the resistance from the water, plug it in here. Take the resistance from the sand, plug it in here. So let me just copy this over. And which are these? 8 and 9 going into 7. 8 and 9 into 7. Copy over the main equation. Instead of the variable we have here, I put in that. Instead of the variable we have here, I put in that. Alright, so this isn't too bad, right? We just broke it down into 3 chunks. Not too many equations if we did that. Now what do we do? Well, now I want to check, do we have enough equations to solve for the variable of interest? Remember, that is the density. This is what we're looking for, the density of the buoy. Okay, so I'm just going to check how many equations do we have, how many unknowns do we have. We know the density of water, we are good. The density, the volume of the buoy, we're good. The gravitational constant, we're good. We don't know this, so that's one unknown. Again, we know these two things, and we don't know this. Okay, those are two unknowns. Here, we know this, we know this, we know this. We calculated this over here, or actually I just listed it up here, so we know that. We know that. Okay, so that's two unknowns still. Over here, the area of the cube, let me write it down here. So area of the cube is base times height, right? That rhymed. Base times height, base times height. So the area is going to be 1 centimeter times 1 centimeter. As I've been doing, I'm going to rewrite that in meters because I don't like to mess around with units. It's not 1 meter, it's 100th of a meter. That's why it says centimeter. 100th of a meter over here. And so we have 100 times 100. We have 1, 2, 3, 4 zeros. So 1/10,000th of a square meter. All right. Let's make sure that I write that down. So the area of the cube is 1/10,000th of a square meter. All right. So we know this as well now. This is clearly constant, so no worries there. Alright, so it seems that we have enough equations to deal with our unknowns. So I'm just gonna have at it. Time to start substituting. I'm gonna label this equation A, this equation B, and this equation C, just to be edgy, because you know I labeled those with numbers and now I'm gonna be inconsistent. So the first thing to do, this is an equation of interest, right? Because this is the equation with the key variable we want to solve for. So I'm going to get rid of any unknowns that I have in this equation. The only unknown I see is the tension. Well, apart from the thing we're trying to solve for, is the tension. So I'm just going to take this formula we have over here for the tension and put it up here. So we're going to go C being substituted into A. So let me copy this over and just take all this stuff that's equal to the tension and put it in here. Alright. Now we have another issue. We have this normal force. We only defined it in equation B. So I'm going to take B and substitute it above. Put B above. Here we are. So let me copy this over. It's getting long and messy, but that's okay because we're just doing simple things. Replace one variable with another. So I'm going to delete Fn here and instead I'm going to put in this stuff. Okay, now we just need to isolate our equation for the unknown variable we're looking for, this one. If it helps you here, you could try substituting things around and then, you know, isolating. For me, I like to save it till the end, so I'm going to do that. So isolate for density of the buoy. What are we going to have? I'm going to try subtracting away all of this mess from both sides so that I only have this term on the right. So I'm going to have this on the left and I'm going to subtract away all of this stuff on the right and the left. So on the right it just cancels out. On the left we have a new subtraction like so. And finally you see, oh, I shouldn't have cancelled that over in the original equation, only in the new equation. So after the cancellation has happened, you saw how we were only left with this term on the right, so we're just gonna put that on the right. Cool. I'm just gonna flip this equation around because I like having the term I'm solving for on the left. So I'm just going to flip it around so that this is now on the left. Nothing's changed, everything's still equal. Now I'm also going to divide by these two terms over here. So I am going to copy this onto a new line, and we are done. When I divide on this side, these things cancel out. When I divide on that side, I have all of this stuff divided by these two things. Finally, plug and chug. Plug in the values that are unknown and we will be done. So instead of doing it here, because it's going to be real messy, I'm going to do it in Desmos so that it's less messy, and just write down the final answer here. So let me open up Desmos. So we have exactly what? So we have the density of the water times the volume of the buoy. So the density of water is 997 kilograms per cubic meter. We have the volume of the buoy, which we said was 1,000 of a cubic meter. So 1,000. What else do we have? Multiplied by the gravitational constant and then multiplied by the, okay, so times 9.81. The area of the cube, I believe it was 1/10,000, though I'll go back and check. 1/10,000 of a cubic meter times 5. Let's just check area of the cube. Yep, 1/10,000 of a square meter, it's an area. Then we have this stuff over here. So the coefficient of static friction, it was given as 0.7 in the question, and it's being multiplied by mass of the cube times gravitational constant. So 0.7 times the mass of the cube is 1,000 of a kilogram times the gravitational constant is 9.81 plus quantity of water times gravitational constant, and what is this? The volume of the rectangular prison. It's 300 thousandths. Okay, so 997 for the density of water times 9.81 for the gravitational constant times, we finally have 300 thousandths of a cubic meter. And that's the top part of the fraction done. On the bottom we have the volume of the buoy times the gravitational constant, so that's 1,000th of a meter, of a cubic meter, 1,000 times 9.81. Is that right? 9.81. Alright, so we get an answer of 975 cubic, well, the units we expect are kilograms per cubic meter. That's what we would expect for a density. Does this answer make sense? We have two ways of sense checking this. First, answer should be less than the density of water, because otherwise, you know, it's not going to float at all. And we know that the density of water, as we plugged in here, was 997. So, okay, on sense check 1, it is plausible that this could be the correct answer. The next thing that we can do is dimensional analysis. Basically just plugging in the units for each of these things and seeing if they cancel out in the right ways. I'm going to do that on Desmos because, again, it's going to be a mess in the equation. So this was kilograms per cubic meter as a density. This was cubic meters, and this was acceleration, so that's meters per second squared. Alright, let me just make sure that's a volume. Yep, we have square meters over here and newtons per square meters over there. So square meters and newtons per square meter. this is a dimensionless ratio, that is the coefficient of static friction. We have a volume over here, I believe. Let's double check that. Nope, that's a mass times the gravitational constant, which is acceleration. So we have meters per second squared for the acceleration, and then kilograms for the mass. This is meters per second square. Another acceleration, we have kilograms per cubic meter for the density, meters per second square for the acceleration. What's this thing over here? It is a volume. Okay, so that's gonna be, let me go back please. So that's gonna be cubic meters. Alright, cubic meters. Down here we have again meters per second squared for the gravitational constant, and finally, what's this? It's volume, so cubic meters. Alright, now let's just cancel some units out. So kilograms per cubic meter times cubic meters. Okay, so that's just, those two things are going to cancel out. Kilograms meter per second squared, that is a Newton. So I'm just going to write Newton. Meter squared times newtons per meter squared. The per meter squared and the meter squared, these two things cancel out, and we're left with newtons. Newtons minus newtons, that's still going to be newtons. Kilogram meters per second squared over here. Let's see, this is going to be newtons, and I think I might have made an error on one of these. Let me just check. So this should be kilograms times meters per second squared. Alright, and then we have, I suppose, a plus sign. Okay, so this is an extra per meters per second squared. Let's just make sure to get rid of that. Now we have kilograms meters per second squared, newtons again, kilograms per cubic meter. Okay, this per cubic meter and this cubic meters, you know, the multiplication and the division cancel out, so this cancels with this. Now we have kilograms times meters per second squared, again newtons. Newtons plus newtons is newtons. Newtons minus newtons is newtons. I'm going to write this as kilograms per kilogram meters per second squared again, because we have a potential to cancel things out. We have a per second squared up here, cancel with the per second squared down here, and we have a per meter down here and a meter up here. Those things cancel, and we're left with kilograms per cubic meter, and that's what we expect. Those are the units. So dimension analysis checks out. So there we have it, we are done. Finally, we have the first part of the question figured out. I said it was hard mode. You clicked on the video, so if you're crying right now, that's on you. If you haven't yet figured out part 2, as I haven't, then go to the video in the link description below, and I will go through part 2 of this question.